Hello and welcome to this video on how to interpret SEM results. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical analysis with latent variables including structural equation modeling, confirmatory factor analysis, multi-level analysis, and latent class, latent profile analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly statistics newsletter as well as workshops that I teach for QuantFish. In this video, I want to explain how structural equation modeling results are properly interpreted, and I will do that based on an example in the Mplus software. You could use whatever software you wanted, of course, to estimate structural equation models, including the free lavaan package in R, for which you also find a mini workshop in the description under this video that is free, where I show how you can get started with the lavaan package and structural equation modeling. In R, I also have a mini workshop in the description on how to get started with Mplus, so check those out as well. And then there are other software programs as well, for example AMES, Listral, EQS, OpenMX, and others. In this example here, I have a latent regression analysis, meaning I have a structural equation model where a latent variable is predicted by two other latent variables. So it's the form of it's a relatively simple structural equation model without an indirect effect here or without a mediator variable. In this case, it's simply predicting a single outcome by two other latent variables, and each latent variable here is measured by two indicators. So you can see here in my model specification I have three factors or latent variables, f1, f2, and f3, and first of all I specified the measurement model here, indicating that f1 is measured by y11 and y21, and f2 is measured by y12 and y22, and f3 is measured by y13 and y23. And then next I specified the structural model or the latent variable model, which in this case is a latent regression analysis with two predictors. f3 in this case is regressed on f1 and f2. So for example, f3 could be life satisfaction, and life satisfaction could be regressed here on income, let's say f1, and then on relationship satisfaction, let's say f2, and to see how much of the variance in life satisfaction can be explained at the latent level by income and relationship satisfaction, and which of the two predictors may be the more important one for predicting life satisfaction. Why would we do this with an SEM and not just simple regression analysis or standard multiple regression analysis? The advantage here is that we're correcting for measurement error in our observed indicators of those three constructs. And so by using two indicators that each may be less than perfectly reliable, we can correct for random measurement error and obtain more reliable results in the structural model, meaning regression coefficients that are not attenuated, not biased by measurement error. If you're more interested in this question of when to use SEM versus regression analysis, I also have a video on this channel on exactly this question. When would you prefer regression analysis versus when would you use SEM? So let's take a look at the output here in Mplus to see what we get and how these results are interpreted. I have descriptive statistics here for the observed variables, which we're not going to look at in detail right now. I want to go straight to the fit statistics so you can see what we should look at first whenever we estimate a confirmatory factor analysis or a structural equation model or also a path analytic model. The first thing that we would always do after we made sure that the model was estimated without problems, we should look at fit statistics. In this case, you can see there's a clear message here that says the model estimation terminated normally, which is a good sign, meaning there was no improper solution here, no estimation problem, no convergence problems. and it seems like the estimation went well in terms of there not being any abnormal parameter estimates, such as, for example, negative variances or correlation coefficients that are above 1 or something like that. This doesn't mean that the model necessarily fit well. So the model estimation may have terminated normally, but the fit of the model to the data may still be poor. So we have to take a look at model fit statistics, and most importantly, we should take a look at the chi-square test of model fit, which is provided under model fit information. When you scroll down a little bit, you find the chi-square test of model fit here, and this is the key indicator of model fit that we should always look at, that we should always report, that we should always pay attention to. And so in this case, you can see the chi-square value here is 8.428, 6 degrees of freedom, and a p-value of 0.2084, which is not statistically significant at the 0.05 level. So if we are testing with an alpha or a significance level of 0.05, then this model would not have to be rejected because the p-value is greater than 0.05. And if that's our alpha level, then we can retain the null hypothesis. We don't have to reject the null hypothesis. The null hypothesis here being that the model fits exactly in the population. So that hypothesis here is not rejected. Now, this doesn't mean that this model is the correct model. It could be that we don't have enough power to reject an incorrect model, or it could be that this is just one of the models that fits this covariance structure, and that some of the assumptions are still incorrect. There could be other models that fit the data similarly well or better, but at least this model isn't rejected. So we have not falsified this model. So it could be the right model for these data. So that's good news. And then there are other fit statistics as well, which here also indicate good model fit. The RMSEA is smaller than a common cutoff value of 0.05. The CFI and TLI are near 1, which would be which is a good sign. And then the SRMR coefficient indicates that the average standardized covariance residual was very small, 0.007. So there weren't a lot of large residual covariances in the comparison of the model implied and the observed covariance structure, which is also a good sign that this model reproduces our observed covariance structure well. So in summary, this model fits the data well, which means it doesn't have to be rejected. It hasn't been falsified, so we can go ahead and interpret the parameter estimates as long as those also look like they are all reasonable, nothing abnormal, no abnormal standard errors. That's also something that we would check even if we find a well-fitting model, because there are situations where a model fits the data very well, but it is over-parameterized, for example, so that you get standard errors that are abnormally high. For example, when you have multicollinearity among predictors, when there are too many predictors in the model, or you have too many factors in your model, where you over-explain, so to say, the data with redundant factors, then that model may look good in terms of model fit, but it may not look good in terms of parameter estimates or estimated standard errors. So we should also check that. And so in the model results section, we obtain then the unstandardized parameter estimates for our structural equation model. And so in that output, we should first of all take a look at those estimates in the first column. Those are the point estimates of the factor loadings, of the regression coefficients in the structural model, of the correlation or covariance in this case between the exogenous or predictor variables, here F1 and F2. And so we should look at these, and we should look at their standard errors to make sure that the standard errors are not abnormally large relative to the estimated parameter values, because that might indicate that there is a problem. For example, if you have factor loadings that have high standard errors to where factor loadings aren't significantly different from 0, as would be indicated by the p-value here at the end, then that could indicate that there's something wrong with your indicators. Or if you find that you have abnormally large standard errors for your latent regression coefficients, then that could mean there's a collinearity problem or some other kind of problem. So always make sure you take a look at the estimates relative to their standard errors. Make sure that those parameters that you expect to be statistically significantly different from 0 really are significant. If they're not significant, then that could also indicate that there is some problem with your model. Where do you find significance or the indication of statistical significance? In the output of most SEM programs, including Mplus, you find typically a test statistic, which here is an Mplus, the third column, estimate divided by its standard error, that yields a Z statistic for a test of significance, testing the null hypothesis that the parameter is 0 in the population. And typically for a factor loading, we wish to reject that hypothesis that the factor loading is 0 in the population because we're expecting significant factor loadings. If an indicator didn't load significantly onto its intended factor, that would be bad. It would indicate that that indicator is not a valid or not a reliable indicator of its underlying factor, and so that could indicate a problem. So you can see that for the first indicator there's actually no such test, because that first factor loading is fixed to 1 for identification to set the scale of the latent factor. Latent factors in structural equation modeling have an arbitrary metric that is not per se uniquely defined. It has to be uniquely defined by either fixing the variance of the factor directly or fixing one of the factor loadings to 1, which is the default in Mplus and many other software programs as well, taking simply the first indicator of the factor, fixing that factor loading arbitrarily to 1. Without, so say, loss of generality. You could also use a different indicator because it's largely arbitrary. And so then the first indicator does not have an estimated loading and has no standard error for the loading and no test statistic. That's fine. But the second indicator does have an estimated loading. You can see it's been estimated to be 0.621. The standard error is 0.024, so it's very small relative to the estimate. So that wouldn't indicate any kind of problem or would not raise a red flag here, because the standard error is very small compared to the point estimate. It yields a large Z statistic because 0.621 divided by 0.024 is a large number, and so that's a very large Z value, and that is highly statistically significant, meaning this second indicator loads significantly onto the factor. Now for the first indicator, of course, we can't make such a statement because there's no test, but it's no trouble, because as we will see later, we can look at standardized factor loadings as well in the completely standardized solution that is also provided by Mplus, and there we can evaluate the loadings for both indicators, because then all variables are standardized, and then we can look at all of the factor loadings and their size. Now, how are these loadings interpreted? They are interpreted like regression coefficients. In linear regression analysis, we have an underlying measurement equation for each of the y variables. That is a linear regression equation that says y11 is equal to an intercept constant plus a constant factor loading, which is shown here, times the factor f1 in this case plus an error term epsilon, an error variable. And so as a result, this is a linear slope coefficient. So this means that by fixing the loading of the first indicator to 1, we say that a 1 unit change in the factor is associated on average, or with an expected 1 unit change in the indicator. So as we move up on the latent dimension of, in this case, for example, income by 1 unit, maybe $1, then we expect that the observed income also goes up on average by $1. And so we're setting the metric of the factor equal, so to say, in a way to the metric of the first indicator. And you can see the second indicator does not have a loading that is estimated to be 1 or close to 1. So that could simply mean that this indicator is measured on a different scale. So here a 1 unit change in the latent factor would be associated with an expected 0.621 unit increase in the value of the second indicator. So it's exactly interpreted like in an unstandardized linear regression coefficient. It doesn't have an extremely useful meaning. In many situations, it's just simply an expression of potential differences in the scaling, meaning differences in the units of measurement between the indicators of the factor. So you could have in an SEM indicators that are measured on very different scales. So one could be, for example, an indicator of income in dollars, and the other one could be an indicator of income in some other unit of measurement, for example, self-rated income in terms of low versus high, that is measured on a 10-point scale or something like that. And so they need not be on the same scale, and the loadings, so to say, adjust for those differences in the scaling of the indicators if there is any. If there isn't a difference in scaling, if you simply had two indicators that both measure income in dollars, then you could set the loadings equal. You could fix them both to 1, assuming what we call essential tau equivalence, where the factor loadings are equal between the indicators. That would make sense whenever you have indicators that are measured in the same units of measurement. When that's not the case, then we estimate the loadings freely, and then there will be an adjustment for the differences in scaling when those loadings are estimated. And so that's pretty much where it ends in terms of the interpretation for those unstandardized loadings. We will later see that the standardized factor loadings actually have more useful interpretation in many cases that tells us something about the reliability or unreliability of the indicators in terms of measures of the underlying factor. So we'll see that in a bit. Next are the unstandardized path coefficients, or regression coefficients, we could say, for the regression of the F3 factor on F1 and F2. So again, the idea was that F3 here may be life satisfaction, and F1 may be income, F2 may be relationship satisfaction, and you can see that here we have a coefficient, a regression coefficient of 0.294 for the regression of F3 on F1, controlling for the covariance between F1 and F2, which is also estimated. And so you can see that that regression coefficient is statistically significant. The p-value here is very small, so there is a significant partial regression coefficient showing that F1 contributes to the prediction of F3, and F2 also does contribute to the prediction of F3 because that coefficient is also significant. Notice that these are unstandardized partial regression coefficients, so here you can't really tell which effect is larger because we don't know really the metric of these factors, and or we can't see that from those coefficients. So if you want to compare the strength of association, then you would look at the standardized coefficients, which we will see in a little bit. After that, we can see that there is a covariance between F2 and F1. So income here would be correlated with relationship satisfaction. In this example, you can see that covariance is positive and it is statistically significant, meaning that the higher the income, the higher the relationship satisfaction on average. Now, how strong this relationship is, we can't see here because this is a covariance and it's not standardized. So it's difficult for us to tell whether this is a strong relationship or a weak relationship, but at least we know it's statistically significant and it's positive. And later on, we'll see in the standardized solution that we get the correlation between those factors, which is easier to interpret. Next are the intercepts for the observed variable. So those are the additive constants in the measurement equation. Remember that for each observed variable y, we have an equation that says y equals intercept plus factor loading times factor plus error variable. And so then these are the constants. And here in this particular case, in this specification, they are simply equal to the observed variable means, because the latent factors by default in Mplus have a mean of 0. And then the intercepts become equal to the means, because when the factor has a mean of 0 and the error term by definition has a mean of 0, then the intercept is the only source of a mean structure in this model. So those intercepts here simply give you the observed variable means, and that's typically not of such great interest unless you're doing a multi-group analysis where you're comparing different groups, where you might be interested in intercept differences between groups for measurement equivalence testing or measurement invariance testing, and or in latent mean differences. If you're interested in that, I have several videos on this channel also on multi-group confirmatory factor analysis and measurement invariance testing. The variances of the exogenous factors are also estimated, and so those give you the extent of, or those provide estimates of the true inter-individual differences on F1 and F2. And then next are the residual variances of the observed variable. So after accounting for the factors, the variance component that remains, that would be attributed to measurement error and or specific variance in each indicator. And for the endogenous variable, the dependent variable F3, we also get a residual variance, because the variance of F3 is a function in this model of F1 and F2. It's predicted by F1 and F2 plus the residual variance. So the variance of F3 itself is not estimated. Instead, its residual variance is estimated. So this is the variance that remains in F3 after accounting for the linear association with F1 and F2. Now, let's take a look at the standardized model results, which are also provided by Mplus. And in this case, I chose the completely standardized solution STDYX, where both the observed and the latent variables are standardized. In that situation, you can interpret the factor loadings as correlations between each indicator and its factor. So for example, the 0.951 loading of Y11 on F1 gives you the correlation between Y11 and F1, 0.951. So it's very strongly correlated, indicating that this is a highly reliable measure of F1. And notice that this loading is no longer fixed to 1 as it was in the unstandardized solution, because now all variables are standardized, and so now the identification comes from fixing the variances to 1 rather than fixing a loading to 1, and now all the loadings can be estimated, and they all here can be interpreted as correlations between the variable and its factor. You can see all 6 loadings are strong. 0.891 is the smallest loading, 0.951 is the largest loading, so those all indicate that these indicators are highly reliable and strongly linked to their factors, which is what we like to see. And then we get the standardized partial regression coefficients for our latent path model. These are now easier to compare between factors, because now all factors are in standard deviation units. They are standardized to a variance of 1. And so therefore we can now compare the relative strength of influence. Here this would mean that F1 in this example has a weaker influence on life satisfaction than F2. Of course, this is not a real data set. This is a simulated data set. So here this would mean F1, if this were income, then income has a weaker influence on life satisfaction than does relationship satisfaction, which has a stronger standardized partial regression coefficient. You can also see that here F1 and F2 are unrealistically strongly correlated, 0.9. So this would indicate that relationship satisfaction and income are very strongly correlated. They're probably not that strongly correlated, I would guess, but in this example, this correlation is very strong. And then at the very end, you get the standardized residual variances, which indicate 1 minus r squared in Mplus, as well as you get the r squared for all dependent variables, including the latent dependent variable f3. Remember that each observed variable is a dependent variable because each observed variable is dependent on its factor. Each one appears in a regression equation where the factor is the predictor. And so we get an r squared for each observed variable, and that r squared has a clear interpretation. It is equal to the squared standardized factor loading for each indicator, and it indicates reliability in the sense of test theory. So, for example, for the first variable y11, we have r squared is 0.904, and that's equal to this factor loading squared. So y11 has a factor loading of 0.951. When you square that, this yields 0.904. And so that's the reliability of that indicator. It means that 90.4% of the variance in the indicator y11 is accounted for by the factor. And we could say that's then true score variance or common variance or factor variance. And so this means that 90.4% of the variance in this indicator reflects true differences between individuals, and only 9.6% would be error variance. Notice that the standardized residual variance is equal to 1 minus r squared. So it gives you the proportion of variance that is due to error, that the residual variance that's not due to the factor. And so this number here plus this number, they add up to 1.0 for that reason. So 9.6% of the variance is estimated to be error variance, 90.4% of the variance is estimated to be reliable or true score variance. And so we can look at that for each indicator. You can see that they are all fairly reliable, all around 0.8. So all have about 80% true score variance, which is decent. And then for the latent endogenous variable f3, the latent dependent variable, we also obtain an r squared, which shows the proportion of variance that is explained by f1 and f2 combined in the latent regression model. And here again, this is unrealistically high. It's based on simulated data. So in this example, 90.2% of the variance in life satisfaction would be explained, which is extremely high. In real psychology, that is probably very rarely seen, an r squared that is so high. I hope you found this video useful to learn more about the interpretation of structural equation modeling coefficients and output. If you did, then please subscribe to this channel, hit the like button. Don't forget to check out the description for additional resources, and I'll see you next time.